Now let's do an example. Let's design a single stub matching network with a series open. The series open means that we have an open circuit on the end of this stub. I'm going to use the same load example that we did before just to make it easy. Remember, there were two places that I could match the real part. So the first thing that I need to do is match the real part of my load. So what it means is that I am going to normalize and plot my load, as you can see here. So plot ZL, and then rotate towards the generator, always towards the generator in this case, until I reach the matching circle. And there are two choices there. I'm going to choose the one which has the smallest d value. The distance that we are rotating is d. That's defining this distance right here, which is the distance between the load and the stub. So the point that I'm going to take is this one right here. I'm going to call that point A. That's the point right here. So this is ZA. Now let's see what distance I actually rotated. I'm going to draw a line through the center of the Smith chart out to the outside edge so that I can calculate distance. I'm going to read off this value, which is about 0.325. I started out at 0.31, so my distance d is 0.325 wavelengths minus 0.21 wavelengths, so my distance d is about 0.115 wavelengths long. The second thing that I'm going to do is read my ZA. And in this case, I don't need to denormalize it. I'm just going to read the normalized value. The real part is 1. It has to be 1 because we just matched the real part. The imaginary part is negative because it's on the bottom. Follow my negative line right here. It's negative 1.4. Now the next thing that I'm going to do is design a stub so that Z of the stub, the input impedance right there at the front of the stub, needs to be the opposite of this value right here. Needs to be minus JX or plus 1.4J. So let's draw that outside. Now that I'm working on the stub, I'm actually going to change color. The stub I'm going to do in red. So when I define L, I'm going to be doing that out here. So let's draw where ZS is. ZS has a real part of 0, so it's around the outside, and it has an imaginary part of plus J 1.4. That means it's above the line. It's right here. This is the ZS value. Now I want to be able to define the distance L until I get to the load of the stub, which is an open circuit. So let's plot the open circuit. Here is Z of an open circuit. Now if I happen to be here at the stub, which is what I've got, and I want to know how long it is, I'm going to be going towards the load. It's the load of the stub. So the distance towards the load is right here, that's red, so it means I'm going to be going this way to get to my ZOC. Now in order to define this length L, the length L, I need to be able to read off my values. So again, draw a straight line out from the center with the point that you're interested in. There are 2 points that are going to be important here. This is like Z input, this is like Z load of the stub. So this value right here is 0.15. The value over here is 0.25. So the distance that I'm going to go is going to be, let's do this in pieces. I'm just going to do this piece first. So L is going to be 0.5 minus 0.15. And now let's do the second piece, which is going to be 0.25 wavelengths long. That is my distance L. So L is 0.6 wavelengths long. Now I've defined my single stub matching network. I've defined my D, that's shown right here, and I've defined my L, that's shown right here. That is how I've designed a single stub matching network with a series open.